So the last effect that we have to look at, which was, although it was of order alpha to the 4, it's much smaller because of the mass of the proton. This could be the hyperfine splitting of hydrogen, and this effect arises because so say that you have a nucleus, it also has some magnetic moment, and there will be some interaction between that magnetic moment and that of the electron. If you recall from, let's say that how you do this, this will give you 1 over 2 E, the Hamiltonian, Q multiplied by the vector potential A, say that, say this is P, minus Q multiplied by some charge multiplied by that. This is the usual maybe I'll ask you to derive this expression, but let's say that there will be some interaction between M dot B. Now the magnetic moment has its own potential, which, if you recall from, I think maybe second year electrodynamics, is given by mu naught over 4 pi. Say that magnetic moment mu. Let's say that, let me use mu cross r over r3. And you know that if given this expression, you know how to get the magnetic field. The magnetic field then will just be I think, curl of A. And if you do everything, maybe I will give this to you as an exercise. You find that the magnetic field that is being set up is given by this. Right? So this would be, say that this would be mu. So to get the Hamiltonian, the hyperfine Hamiltonian, you just have to dot this. Right? So this is mu 0. So, but you know that mu proton is given by that. Now this G factor you can measure, it comes out to be 5.59. The one for the electron, as I keep saying, is not really true, but so you get minus E over M as electron. So once you start dotting stuff, you will end up, because this mu P, which is the one sitting there, you have to dot it with this one, but it's expressed in terms of SP. Similarly, that is expressed in terms of SE, and this is ME and MP. So once you express or substitute everything, you end up with dot product between SP dot R, SE dot R minus SP dot E. Right? But we only want to find the energy corrections due to this hyperfine Hamiltonian. Right? So this, as you know by now, this will just give you the expectation value. So this gives you mu GP E squared over 3 MP ME. Anyway, this is just a constant. So the only thing that you have to be considering will be this SP dot SE delta 3 of R. And by now you know how to compute this expectation value. So you might get something SP dot SE, but this will just be some hydrogenic atom, like maybe, let me just call it NLM squared, right, D3R, but it's being acted on by this Dirac delta function. So what is the end result? This just gives you the value evaluated at 0. So you end up with something like psi 0 squared. Right? So that part of the hyperfine energy correction will just be proportional to psi 0 squared. Right? This term. So is everyone happy with how I obtained that term? It's just you are integrating, you want to compute the expectation value, evaluate in terms of Dirac thing, and this is usually called the spin-spin, in contrast with spin orbit coupling. But for some reason this is 0, and I want to show how that is done. Maybe I should leave that as next. So let me change slides. So I'm saying that there will be that complicated part which is coming from mu b dot this thing, but once you try to calculate this, you get 0, and so that's what I want to show. So the only term that would be left will be this one, which will be proportional to this delta function, delta 3 of r, and once you evaluate that, you just get psi 0 squared. So let's see, share whiteboard. So the way that you do this, you want to compute. Again, this is one of these missing integrals similar to what you are doing, but because I'm no longer interested, like I know that you can do this integral, so this won't be part of an exercise, which is why I think it's best if we just show that other part with sp dot r 0. So let's just define this a hat dot r, b dot r hat sine theta d phi. So if you write everything out, you get, remember, this will give you ax sine theta cos phi, right, plus ay, just write everything out, sine theta sine phi, plus ay cos theta. You know how to write r, just the unit vector will just be, it will be depending on these angular parts, right? So you do the same thing for the b dot r, so you get bx sine theta cos phi plus the same expression, sine theta sine, I think this is sine phi, this is sine phi, plus ay, I think this is b z cos phi, right? And you can check that the integrals maybe sine phi, say 0 to 2 pi of d phi, it's the same as the integral for cos, right? Which is the same, because you get, they will give you 0. So the only thing that tends to be remaining once you try to do the integral, remember that there's an integral d theta sine theta d phi. Once you try to do the integral over d phi of most of these terms, because the integral of sine phi d phi is the same as the integral of cos phi d phi. So for example, if you try to multiply this term with the term coming from so let's see, you get ax bx. So the ones that will be contributing, once you try to do the integrals over, you start by doing the integrals over d phi. So this will end up giving you this term here. So this gives you sine squared theta cos squared phi plus ay by sine squared theta sine phi. You get az bz, right, which is this term. The other terms you can check that they do vanish. So this gives you bz cos squared theta, right? But all these things I shouldn't have included this. All the terms are being multiplied. There was this sine theta d theta the background, and then you make use of integral of sine squared. So because now you want to integrate out this, so let's say that integral sine squared theta goes to integral of cos squared, say phi, because remember that this still that d phi and 0 to 2 pi, 0 to 2 pi. This is the same as this. You can check that this gives you pi. Similarly, the other one is trivial. It's just d phi from 0 to 2 pi gives you 2 pi. So most of these integrals you can do. Let's see. Just check that what you end up with will be after some work. Maybe in the slides I'll include this computation, even though it's long, but in the end what you get is 4 pi over 3 of a dot b. So if you look at the term that was there was 3 s dot r with a p s e dot r minus sp dot se. You had to calculate this expectation value with respect to r cubed, and I've just shown that this part of the integral was given by, say, this was a dot r with b dot r hat. This is just given by a dot b, right? So although that expression was for general case, you can also set a to be sp and the other one to be se, and this gives you 3 times. You're basically using this result. The integral of a dot r hat b dot r hat is given by 4 over 3, right, of a dot b, but there's also this 3, so you end up with 3 times 4 pi over 3 a dot, a in this case is just sp dot se, right? Expectation, but that 3 will cancel with that 3, and this integral, I'll write everything out. Once you do it, you will just get the integral over the what you call this d omega, which will give you 4 pi. So that term will cancel with this term, and you get 0. So the hyperfine contribution only has one term, which is the one that is proportional to psi 0 squared. Right. Let's go back to the slides. Right. So, and we are done. I think in the slides I'll also include this, or maybe a summary of the calculations that I did. So for the Clebsch-Gordon coefficients and also this term. So this term, you can show that this is 0. You're only left with this one. Now for this one, by now you know how to deal with things that have s dot p as p dot se, right? So if you remember when we had L dot S, you looked at the angular momentum, right? So total angular momentum was L plus S, and then you squared that, and then you expressed maybe L dot S. So you're going to do the same thing here. So the total angular momentum of the system will be due to SP plus SE, right? And then if you square, you can see that if you square the total angular momentum, you get SP squared plus SE squared plus the term that you're looking for, 2SP dot SE. And then you can solve for this term, right, which is the term sitting there. So if you solve, you get this. Now, let's say that you can have this case. So this is proton and neutron, both of them spin half. So you can have this state, say S equals to total angular momentum being 1. This is a triplet state. You know that if your J is given by, let's say, in this case 1, right? So you know that you can have M, L, or in this case MJ will be going from you get -1, 0, and 1. So this will be a triplet state. The other state maybe when you have S equals to 0. Right? So this part will evaluate into two contribution. Either the part when you have S equals to 1, or the total angular momentum being 1. But you know that it's what I wanted to say in the first lecture. When this adds, it gives you L plus 1 h bar squared. So for this case, you get 1. So this will give you 1 plus 1, which will be 2. So we'll get something which will have S squared to h bar as E, right, has angular number 3/4, right? And they are the same. So you either get 2h bar squared minus this, or you get the term that has 0, right? Because if you put 0 there, or maybe I should use S times S plus 1, then you get the other contribution. So if you put everything together, you get, there will be, let's look at S equals to 0. Let me try everything. So when S equals to 0, right, that's not there. And then you get 2 of the same factors. So you get 2 times 3/4 squared, but they're going to cancel. So you are left with only the 3/4. So the singlet state S equals to 0. So this singlet just means S equals to 0, gives you the 3/4. The S equals to 1, you can check it's the 2h bar squared minus the other contribution from SE squared minus SP squared will give you that state there. And you can measure, it's similar to the Lamb effect, right? So you can measure the energy difference between the triplet state and the singlet state. And this, I think this was done by Pucel and Owen. So let me say, I think it's Pucel and Owen. Right. Basically, you want to measure the energy difference between these two. Right. So it's just the difference between these two. So this will give you, say, -2/4, -1/4, which just gives you a -1. So this is the energy difference. And you can also express this in terms of, as I was saying, that this is the energy difference between the triplet and the singlet state. And you can also write it in terms of the wavelength, which gives you that 21 centimeter. And this 21 centimeter is very famous in radio astronomy. The next thing that we are going to do will then be to move to chapter 8, which is another method to compute. So to remember that in this chapter, what we wanted to do was to calculate this energy correction. And for example, maybe the first order correction was just given by psi n, h, psi n. But in order for us to do this, we relied heavily on the fact that we had solved the part of the Hamiltonian. So we knew what the energy eigenstate for the unperturbed state was. However, in general, we don't know. So even in general, we don't even know how to solve for these things. And what the next method does, but it might be that we are only interested in the ground state. Right? So what you do is that you guess any trial wave function, any. So the famous ones that we will be using will be things like the Gaussian. You can guess any. And what this will do is that the ground state of your system will always be bounded. So by say that maybe let's call this trial, whatever trial wave function that you list, it will give you an upper bound for your ground state energy. And if you choose these trial wave functions very cleverly, you might actually even saturate this bound and find that whatever you guessed, it's actually the ground state energy. So the first thing that I have to prove is that if you take any trial wave function, that the expectation value that you get will always be an upper bound. So that's the first thing that I have to check or prove before we can make use of this thing. So this is covered in the next chapter, which is chapter 8. Let's see. Hopefully I did upload this. So this method works very well because we don't really have to even solve the Schrodinger equation, and most quantum chemists actually make use of this thing. We just guess some trial wave function, use that trial wave function to compute the expectation value of H using this trial, and you will always get that it will give you an upper bound. So let's prove that. So how do you do that? So you know that, let's say that the eigen functions of H of your Hamiltonian, they will form a complete basis. So this means that whatever trial function, so maybe I should have written psi t, whatever trial wave function that you choose, right, you can expand it. This coefficient will be unknown. You can always expand it in terms of the eigenfunctions of this H. Right? So the first thing that you have to check will be, let's say that they were normalized. So normalization is not really an issue because we went through this step that if someone gives you a basis that's not really normalized, you can use Gram-Schmidt. So normalization, if they are not normalized, you can normalize them. So let's just assume that you have normalized them. So let's write everything out. Now, as I said, that this can be written in terms of the eigenfunctions of H. So you get N C M, let's use M, psi M, and similarly, but now you have to use another Delta variable, which I chose to be M, so you get Cn psi N, right? Now these are just sums, and most they should be linear, so you can take them out of the expectation, so you end up with a sum over M and N of the same with the coefficient Cm, Cn. I think if you take things out of the first Dirac bra, you get a complex conjugate because usually we are working in C, not R. And then you will be left with psi M, psi N. And what is psi M? What is this? So these vectors are eigenfunctions of your Hamiltonian, even though you don't know them, but you always assume that they are orthonormal. So if they are orthonormal, that means that they should give you the Kronecker delta. So this gives you delta M N, sum M N C M. This is not M. This is the Cn there. So this is a Cn, Cn, And then this sum, just let me write it here. So this sum simplifies into it's 0 unless m and n are the same. So this just gives you Cm star Cm, which is just sum of Cm, the mod of Cm. So we've just proven that 1 equals to this sum, right? Which is not what we actually wanted to prove, right? Remember that we want to show that whatever trial wave function that you choose, it will always be an upper bound. So now let's see what happens when we include the Hamiltonian into this overlap. So the expectation, just for now, just remember that the sum of these expansion coefficients will give you 1. So if you then, let me clear everything. So now we repeat. Okay. Right. So as I was saying, we want to find the expectation C expectation value of h as computed in terms of this trial wave function. So this will give you sigma m cm psi m, but we still have the Hamiltonian h acting on cn psi n, right? And then we know that h acting on psi n, what does that give you? Right? We're just repeating the same procedure. So Cm star Cn, right? We're left with psi m. H acting on psi n gives you En psi n. This is just a C number, so you can also take it out. So this gives you Cm, keep writing Cm star Cn, right? En, you're left with psi m psi n. And again, what is this? Again is the Kronecker delta, right? So you are left with sum over m Cm Cn En delta Mn. So this gives you sigma m Cm mod squared, right? This gives you a mod, and you're left with Em, right? So we have just shown, let me think, okay, before I erase everything, let me just summarize what. Is everyone happy that we've just shown that the trial Hamiltonian, or the expectation of the Hamiltonian, is going to be given by Cm Em, this part here. But by definition, right? So if you define, say that this is your ground state. So your ground state is the lowest energy state. So you might have other states, say this is En, but any nth state in terms of energy, let's say Em, because of rewritten, it's always greater than E ground state. So even if you were to take the sum, say sigma Cm squared Em, this will be greater than Eg, than the sum of Eg Cm squared, and then you can take out the Eg out. As yeah, I think I've written it there. Is everyone happy? If you have the ground state, any other mth or the 43rd one, it's always higher by definition. So Em is always bigger than E ground state. And then I just take the sum. So you get sigma Em Cm squared. This has to be greater than sigma Em or E ground state multiplied by Cm squared, which is what I'm writing here. Just this expression following from the definition that the ground state is the lowest state that you could ever get. Right now we take this out. Right, this just gives you E ground state sigma M C M squared. And what is this? Remember that this proof that the trial wave function will give you an expectation that is bigger than everything. It consists of two steps. Right? So in the first step, we showed that the sum of the normalization coefficients was equals to 1. So this is just 1. So this falls away. And you end up, if you look there, the expectation value of that, this will be greater than or equal to the ground state. So if you want the ground state, it's always bounded by whatever expectation you get for the Hamiltonian using any trial wave function. So to check how this method actually works, right? It's like the harmonic oscillator is the perfect example for all things. So even in the previous chapter, we were using the harmonic oscillator even here. And the best candidate for these trial wave functions is always the Gaussian. So I'm just going to take psi 0 to be a e minus alpha x squared. The first thing that I have to do is to try and normalize. And if you do that, again, this is cut off, but I think you can check that this is just 2 alpha over pi to the 1 over 4. The point is that whatever wave function we use, we have to try and calculate what is this h, right? Which would be, so you know by definition, this would be psi 0 h psi 0. It's what you were doing in the tutorial. Right. So you plug in the psi 0, right? This is squared e to the minus r a alphas x squared, right? Then we just differentiate this twice, right? So if you differentiate e to the minus alpha x squared, first you get minus with respect to x, you get e to the minus alpha x squared minus alpha, right? And then once you differentiate it again, you will get two, let's just see, with an x there, right? So once you differentiate it twice again, you will get the term e to the minus alpha x squared, which will be this term. It's coming, just check that that minus is that one. But it can also, this derivative can also act there, which will just give you the term which is alpha. And then this term comes from there. And once you simplify everything, you get the expression for this 0. Right? And this method then once you have this expression, you want to minimize it. Right? So then you take d is 0 over d alpha. Remember that this alpha is a variable, but you want, and whatever variable, this thing will be an upper bound. So it's E ground state, it's smaller than or equal to E naught alpha. But you want to minimize this so that this upper bound is getting closer and closer to this EGS. And you know how to do that from first year. You just extremize it by taking derivative with respect to this alpha. So this, and then you set this equals to 0. So it's a very simple method to use, because then you find what the expression for alpha will be. So that this gives you alpha squared. Then you solve for this alpha. The alpha that will maximize this, plug it back there. So if you solve for alpha and plug it back into your find that alpha 0 is given by m omega over 2h bar, and then you plug it into the wave function. Remember that the wave function was, I think it's 2 alpha over pi v 1 over 4 e to the minus alpha x squared. Whatever value for e0 that you get, you go back and you plug it there and you simplify. And then for the energy, you take this value for alpha 0 and you plug it back there. And you can check that the energy that you get, it's actually the exact one. So this method works, but I think for today, in case I tend to overload people, I think I'll stop here. So what I will do the next time will be, I will then try to compute the excited energy. So I've just computed the ground state, or try to minimize the energy, and I found that I got the exact energy level. But the next thing that I will be doing will be to try to compute E1 and E2, and then try to make use of this method to find the ground state for helium. I think today I'll end here. Are there any questions? Okay, then I'll see you on Thursday then. And before I stop recording, as I said, the homework assignment is due on Friday, so you have to submit by or before midnight on Friday. Okay, see you on Thursday.